All right, good day everyone. So today we will be discussing a new topic which will be part of our formative assessment this coming Friday. So anywhere in the video you can pause, take down notes, or if not, you can go back to any parts and try to listen it to again if in case there is a need to. Let's begin. I'd like you to recall on how we were able to find the area under this particular curve, which in this case is a line. So if you try to recall our process, we try to find the upper and the lower boundary, which in this case is from 1 to 4, and we try to find the integral of the function, and later on, that's when we evaluate the function given the boundaries. Okay, so this is what we did before. Okay, now this process is possible if you know the function and if you know, let's say, the boundaries of the portion which we wanted to find the area with. For example, in this case, we wanted to find the area of the region bounded by the curve, which in this case is f of x equal to negative x plus 6, x equal to 1, x equal to 4, and of course the x-axis. All right? Now, similarly, we did the same thing given this particular situation, which in this case, we are looking for the area bounded by the two curves, the one in red and the one in purple, and of course, x is equal to 3. So the same process, we tried to find the boundary, which in this case is from negative 1.37 up until x equal to 3. And we tried to find the difference between the curve found above and the curve found below. So it would now be this curve, which is square root of x plus 2 minus this curve. And we found the integral, and we were able to find the area, the approximate. It's only an approximation, which is 6.08. Again, all these are possible because we know the boundaries and we also know the region that we are focusing with. Now, what if you are given, let's try to apply it here in this example. So similar process here, we know that this is the curve, okay? And this is the area we're looking for, the region under the curve bounded by A and D. So if you try to analyze it carefully, A here is actually equal to x equal to 1, and B here is equal to x equal to 6. Now you may pause this video and you may try to see and look at, or you may analyze for you to be able to understand that these are our x values. To continue, we do the same process, integral of the function. Since we have a function here, the topmost function as the curve y equal to 12 over x, and the bottom function which is just equal to y equal to 0, thus it's just the same as 12 over x. So continuing the process, we now get the value 21.50. We will use this to compare another method of finding an approximate area of this. However, this method is applicable for certain situations only. Like, what if there's no function given? What if you are just asked, what is the area of the region bounded by the curve, the x-axis, and the two other values of x? So in this case, we can still find the boundary, by which we could still say that the boundary is, let's say, 1 to 6. All right? However, we cannot proceed with the method we previously know because we do not know the function itself. All right? However, if you try to recall, there was a way I introduced before. That was the introduction of integral, by which we can actually somehow approximate the area by coming up with smaller rectangles. The smaller the rectangle, the smaller the error would be. And the more area is being covered. So meaning we could also apply that process here, by which we can come up with rectangles like this. However, if you try to look at it, if we push through with this method of coming up rectangles, you can actually see some portions here which are not totally covered. All right? And the bigger the portion which is not covered by this method, by this rectangle method, the bigger the error would be. We wanted to come up with an approximate close to the real value. Thus, this method, the rectangle method, may not anymore give us an accurate answer. So what could be another way of getting an approximate which is closer to the real value? Now, in this case, we could still use a certain quadrilateral, something that will allow us to cover the most area. And this quadrilateral would be a trapezoid. So instead of a rectangle, we can actually instead use a trapezoid in order to approximate the area. So if you try to look at this one, instead of a rectangle, we have here a trapezoid. So this will be the first trapezoid, T sub 1. So the slant, this is now a slant side, not anymore a straight one. All right, so we have series of trapezoids here. And if you try to compare the two methods, the trapezoidal method or the method using trapezoids would limit the error. Yes, there might be areas that are not covered, or there might be areas that are overly covered, meaning it goes beyond the curve. But then if you compare this with the previous method, the error here is much lesser. Thus, the second method is by using trapezoids instead of rectangles. Now, again, this method is only applicable, is practically applicable if there is no given function. But if there is a given function, you could still use this method, or you could use the ones we used to have, which is finding the integral. Okay? Pause this video, take down notes if it's necessary. Let's proceed. So we call this the trapezoid or the trapezium rule. Remember, to find the area of a trapezoid, it's just equal to half of the height. And here the height is the distance between the two parallel sides. In this case, the parallel sides of the trapezoid is A and B. So again, half of the height times the sum of the length of the two parallel sides. Okay, so this is the area of the trapezoid. So if we try to apply this area here in our graph, in our method, in our curve, we can actually find here 5 different trapezoids, by which these two are the parallel lengths or parallel sides, which is just represented by your y relative to the x-axis. Okay, these are just that the length of this will just be the y values. In this case, it's 6. In this case, it's 12. And of course, the height, which is technically just the width. So in the trapezoid, we call this the height, the distance between the two parallel lengths. However, if you try to look at this in the perspective of the graph, this looks like a width, not the height. So you can just interchange the two quantities for as long as you understand and know what quantity you're referring to. It's not a problem. So in this case, the height, or simply the width, is just equal to the x value, or the x interval in this case. Not the x value, but basically the x interval. So if you try to look at it, this is equal to 1 unit. All right? So continuing, if we try to apply the method of the trapezoids to find the approximate area of this, we can actually find the area of the individual trapezoids, starting from the first trapezoid, T sub 1. So that would now be before that, by the way, if we try to put labels here, this is our first length, vertical length, second vertical length, third, fourth, fifth, and sixth, just for the sake of putting labels. So we have 6 different lengths. But then, since we have 5 trapezoids, we can actually adjust these labels, because they're just labels, we can actually modify them so that we will be reminded that there are 5 trapezoids. Instead of starting with 1, I can start with 0. So I can say this is y sub 0. This refers to the first length. Y sub 1 refers to the second length. Y sub 2 refers to the third length, and so on and so forth. So I'm just trying to modify it so that my last y would be y sub 5. And this tells me that there are 5 trapezoids. Okay? So again, these are just labels. But these labels are actually used internationally. So you could also use them, make use of them. So again, going back, so we have to find the area of each trapezoid and then add all of them. That's the area of the entire region bounded by this curve and, of course, the x-axis. So finding the area of each trapezoid, it would now be, first trapezoid is having an area of half times the x, remember this is your width or height, times the sum of the two parallel sides, y sub 0 and y sub 1. And then the second trapezoid would have this area, third trapezoid, fourth, fifth. At this point, pause the video so that you can analyze well, you can copy notes, and you can understand. Now, since we have found already the area of the individual trapezoids, we can now find the total area, which is just adding all of them. So the total area would now be the sum of all the individual areas, which will just be this. So I tried to make it color-coded so that you would know that this is the area of the first trapezoid, second, third, fourth, and fifth. Now, to continue, if you try to inspect, it's very long, so we can shorten it by trying to factor out common factors, if there are. So here, you can observe that each of them contains a factor of half x. So we can factor it out, thus we will have half of x times the remaining. Okay? So we now have this one. However, we could still modify it because you can actually see that there are parts which are being added repeatedly. So we can just modify this by saying that this will just be half of x times y, half of x times the quantity y sub 0, y sub 5, plus y sub 1 is added twice, so we can just write it this way, 2 times y sub 1, 2 times y sub 2, 2 times y sub 3, plus 2 times y sub 4. Or if you want to really modify it, we could also write it this way. All right? And this now gives you the trapezium rule. Okay? So this is now what the trapezium rule, and this is now somewhat the formula or the notation on how to find the trapezium rule. Let's try to apply it in some of the examples. All right. Now remember that, by the way, before that,